Hello, and thank you for joining me on this video of atoms and nuclear radiation. In this video we're going to talk about radioactive decay and nuclear radiation, and then we're going to move on to nuclear equations. Before we begin, we should just do a quick recap on atomic structure and isotopes. So we use the nuclear model of the atom, and in the nuclear model at the centre there is the nucleus, and this contains the protons and the neutrons. The electrons move in their orbits around the outside. I'm sure you remember that the relative mass of a proton is 1, of a neutron is 1, and of an electron it's almost 0. The relative charges of a proton are +1, a neutron is 0, and an electron is -1. The definition of an isotope is something that has the same number of protons but different numbers of neutrons. So as it's got the same number of protons or the same atomic number, it's the same element. If we look at the example of carbon, you've got two isotopes of carbon. There's carbon-12 and carbon-14. Both have 6 protons, which again shows that they are the same element. But carbon-14 has got 2 extra neutrons, which means it's slightly heavier than carbon-12. This means that the nucleus may be slightly more unstable, and we'll talk about that more on the next slide. The isotopes of some nuclei can be unstable. This is when the nuclear forces can't hold the nucleus together. To become more stable, the nucleus gives something out, and this is a form of nuclear radiation. This process is called decay, and it happens completely at random. There is no way in which to speed it up or slow it down or prevent it from happening. It's a completely random process that cannot be predicted. You need to know about 4 types of decay. The first is alpha. This is where the nucleus gives out 2 protons and 2 neutrons. There's beta decay. This is where a neutron turns into a proton and an electron. The electron is emitted from the nucleus and the proton is kept. Gamma decay is the third. This is when energy is released from the nucleus in the form of high-frequency electromagnetic radiation. And the fourth type is neutron decay. This is where a neutron is given out from the nucleus. For your exams, you need to know about the properties of alpha, beta and gamma radiation. You need to know their symbols, their penetration through materials, their range in air, and their ionising power. Ionisation is when an atom which has a neutral charge, that is, that the number of protons, which are positive, is balanced by the number of electrons, which are negative. And this is then turned into an ion, which is a charged particle. This can be achieved by either gaining or losing electrons. In nuclear radiation, we are only talking about losing electrons. They're knocked off by an alpha particle, a beta particle, or energy from gamma radiation, giving the electron enough energy to completely leave the atom. This means that there's an overall positive charge, as there are more protons than there are electrons, so you end up with a positively charged ion. You need to know the symbols for alpha and beta radiation, and for this we use nuclide notation. An alpha particle is made of 2 protons and 2 neutrons. This is the same as a helium nucleus, so we can use He as the symbol. The atomic number is then 2 for the 2 protons, and the mass number is 4, as there are 4 things within that alpha particle. A beta particle is made of electrons that have been ejected from the nucleus because a neutron has turned into a proton and an electron. The electron has almost 0 mass, so we use 0 as its mass number, and we use -1 as its atomic number. This is nothing to do with protons, it's just when you do the nuclear equations, it makes the maths a little bit nicer. Gamma uses capital Gamma from the Greek alphabet, or you could write the word gamma in your exams. Penetration through materials is how far alpha, beta and gamma radiation will actually travel through a material. Alpha is the least good at travelling through materials and will be stopped by either paper or skin. Beta is the next least good at travelling through materials, and it will be stopped by a few millimetres of aluminium. Gamma is the best at travelling through materials, and it will only be stopped by thick lead or thick concrete. Their range in air also reflects their ability to penetrate through materials. Alpha travels only a few centimetres, beta about 1 metre, which is handy for revision as it rhymes, and gamma, because it will only be stopped by thick lead or concrete, has an unlimited range in air. Alpha has the highest ability to ionise as it is a large particle and it is the most likely to be able to knock an electron off an atom and turn it into an ion. Beta's ionising power is less than alpha's but greater than gamma's, and gamma is the least ionising of the three. Radioactive decay can be represented as nuclear equations. These show the starting unstable isotope and what happens after the decay process. The following examples are specifically mentioned on your specification for AQA, but you may be given different ones in the exam. In alpha decay, we're going to start with radon gas. Radon gas has an atomic number of 86 and an atomic mass of 219. This decays by alpha decay and gives out a helium nucleus, and we've got the symbol there, He42. As it decays, it gives out 2 protons, so the atomic number goes down from 86 to 84, and the atomic number 84 means polonium. The mass number, the atomic mass, this goes down by 4 as there are 4 things given out in alpha decay, 2 protons and 2 neutrons. So the atomic mass goes down from 219 to 215. In beta decay, a neutron turns into a proton and an electron. The electron is ejected from the nucleus, and you can see that the beta particle there, represented by the E and the 0 - 1, is present on the right-hand side of the equation. As the carbon-14 has decayed, it has lost a neutron but gained a proton. So overall, the mass number remains the same, which is why you get 14 on both sides of the equation. The atomic number, however, has gone up by 1 because the previously carbon isotope has now turned into nitrogen. And nitrogen has an atomic number of 7. For both types of equation, you need to make sure that the numbers on the right-hand side and the numbers on the left-hand side add up. So in alpha decay, 215 plus 4 gives 219, and 84 plus 2 gives 86. In beta decay, when we're talking about the atomic mass, we've got 14 on the left-hand side and then 14 plus 0 on the right-hand side, which gives us 14 overall. And then for the atomic number, we have 6 on the left-hand side, and then on the right-hand side, we've got 7 plus -1, which gives us 6. And that's it for this video. Thank you very much for listening.